Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber, to give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience. Special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection, a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/1600 to 0.4 of an inch, are suitable for sturdier products like structural elements or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end to end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Hey bro! Today, we're diving headfirst into the wild world of money. Straight to the US Bureau of Engraving and Printing. That's the spot where real deal dollars are born. The ones that end up in people's pockets and keep the global economy humming. But listen, these aren't just some random pieces of paper with numbers slapped on them. Every bill is a legit masterpiece, packed with cutting-edge tech. We're about to uncover the secrets behind that one-of-a-kind paper, the mind-blowing microscopic details, and the top-tier security features that make the dollar untouchable. You ready? Let's roll. This is gonna be epic. First off, forget about regular paper. Dollars are printed on some next-level stuff made by Crane and Company. This isn't your basic white office paper. It's a cotton linen blend with a unique texture that's totally different from the usual. That's why dollars have that crisp crinkle and last way longer. The material is 75% cotton and 25% linen, with tiny colored fibers woven in that you can only spot under a microscope. Plus, the paper is packed with watermarks and embedded security threads, making it nearly impossible to fake. This paper gets delivered in massive rolls, each one guarded like it's gold. And boom, that's step one in the battle against counterfeiters. Now we're stepping into the engraving department, the place where the magic happens and the main design for each bill is born. This is where artists, known as engravers, carve out the intricate designs and portraits by hand on metal plates with jaw-dropping precision. Take those iconic presidential portraits, like George Washington on the $1 bill or Benjamin Franklin on the $100 bill. They're painstakingly recreated from photographs. And those lines that look straight? They're actually made up of microscopic details. That's another layer of protection. No regular printers pulling that off. Feeling a little outclassed? Don't sweat it. This stuff is straight up genius. Next up, we're heading into the heart of the factory, where the real magic of printing goes down. Check out those massive printing machines using the intaglio technique. That's fancy talk for deep engraving. Here's how it works. The metal plates made by the engravers are coated with ink, and then the excess is wiped off, leaving the ink only in the engraved grooves. The paper is then pressed onto the plate under insane pressure, transferring the ink onto it. Thanks to intaglio printing, certain features on the bills, like the portraits, have a raised texture you can actually feel. How cool is that touchable detail? This process happens multiple times because dollars are printed in layers. First comes the black ink, then green, and finally, other security features are added. Every year, they crank out about 7 billion bills here, with 95% replacing old or worn-out cash. Oh, and the ink? It's so tough that even if you bury a dollar bill for 20 years, you'd still be able to recognize it. In today's world, where counterfeiters are getting slicker by the day, money has to level up with serious protection. For instance, there's microprinting, tiny text you can only see with a magnifying glass, added around portraits or borders of bills. It's so small and detailed, it's practically impossible to fake. Then there are those special security threads embedded in the paper. Under ultraviolet light, these threads glow in different colors depending on the bill's value. For example, $5 glow blue, while $100 shine pink. And let's not forget the $100 bill. It's loaded with high-tech features like 3D holograms that shift and change depending on the angle you look at them. How's that for next-level security? Next stop, the offset printing section. This is where those background images, like the green and golden hues you see on dollars, are added. It's the second line of defense. Intricate patterns and color gradients that are almost impossible to replicate with basic tools. Rolls of future cash spin on cylinders, feeding into the printing machine. Once the ink is applied, the rolls are cut into sheets of the perfect size. Fun fact, a dollar bill lasts on average 5 to 8 years before it's retired. On the back of the $1 bill, you've got the pyramid symbolizing strength and durability, while the all-seeing eye represents divine protection. Pretty wild, right? Let's keep this tour moving. Bro, now we're in the room where dollars get their names. This is where each bill gets its unique serial number, printed in either black or green ink. It's basically the ID code for every single banknote. The next step? Stamping the Federal Reserve Seal. These seals show which of the 12 Federal Reserve banks issued the note. This whole process happens on high-speed printing machines that churn out thousands of bills per minute. And get this, the printing conditions are no joke. The machines apply 80 tons of pressure, and the wax-based ink is literally baked into the paper under high heat. The ink is specially designed to resist wear and tear, even something as wild as going through the wash. Oh, and here's a crazy stat. The total value of all cash dollars in circulation is over 2 trillion. How's that for some money talk? Before dollars leave the factory, they go through some hardcore quality control. High-tech scanners check every single bill for defects. Blurry ink, damaged paper, or misaligned designs. If there's any mistake, the bill is pulled out of circulation immediately. The ones that pass, they're neatly packed into stacks of 100 bills. The final step is packing the money. These stacks are loaded into special containers and shipped off to Federal Reserve banks. From there, they make their way to commercial banks and eventually into people's hands. The whole transportation process is locked down tight, with heavy security. We're talking millions of dollars here after all. When a bill is declared too worn out, it gets destroyed. Don't get teary-eyed, bro. Let's check out how it happens. Worn-out banknotes are tossed into industrial shredders that chop them into tiny bits. According to the Federal Reserve, around 5 billion bills are shredded every year, mostly $1 and $5 notes, since they take the hardest beating from daily use. But shredded cash doesn't just get thrown away. The Federal Reserve is big on keeping things eco-friendly, so they find ways to repurpose the materials. Here's a funny story. One time in Texas, some clueless criminal broke into a Federal Reserve facility, thinking he'd hit the motherlode. Instead of stacks of cash, though, he walked off with a giant bag of shredded money. Thinking he'd scored big, he dragged his loot home. Spoiler alert, shredded cash is worth zilch. The guy got caught within a day. Tough luck for him, but at least we got a good laugh out of it. In some states, shredded bills are pressed into dense briquettes that are used as fuel for energy production. Pretty cool, right? This process replaces wood or coal, cutting down on environmental harm. In areas with the right tech, the shredded cash can even be turned into compost, since cotton linen paper is biodegradable. Yeah, money literally gets buried in the ground. A portion of the shredded banknotes is also repurposed into souvenirs. For example, they're packed into clear balls or boxes and sold to tourists at gift shops in the Bureau of Engraving and Printing. It's a unique way to hold a piece of money history in your hand. So, how about it, bro? Want to snag a chunk of chopped up cash for your shelf? Destroying large sums of cash is a whole other level of operation. When entire series of banknotes are pulled from circulation due to design updates or new security features, the disposal process gets even more intense. The old bills are transported in armored vehicles under strict surveillance, and every step of the destruction process is carefully documented to make sure not a single bill ends up in the wrong hands. This massive operation is actually cost-effective in the long run. For instance, according to the Federal Reserve, the cost of destroying a single bill is just 0.03 of a cent, thanks to automation. Every day, up to 200 tons of banknotes are shredded across the US. Even the machines used to destroy bills are guarded as tightly as the money still in circulation. It's a big deal, but hey, with that kind of precision, counterfeiters don't stand a chance. When it comes to durability, $1 bills last about 6.5 years on average, while $100 bills can stay in circulation for up to 22 years since they're handled less often. Not bad, bro, especially when you compare it to the lifespan of large denomination euro bills, which is only about 5 years. So, how do they decide when it's time to retire a bill? That's where the Federal Reserve's specialized machines come in. These machines assess the condition of banknotes and flag the ones too worn for circulation. But here's the kicker. The actual disposal doesn't happen at the same place as the printing. The Bureau of Engraving and Printing only destroys defective bills that pop up during production. For example, if the ink isn't applied evenly or the paper gets damaged, those bills are immediately shredded. Quality control on point, right? A few years back, a group of criminals in the US decided to rob an armored truck carrying cash. They planned the heist down to the last detail, but they picked the wrong moment to strike. Instead of shiny, fresh bills, the truck was hauling worn-out banknotes headed for destruction. The plan might have seemed genius at first, but the payoff? Practically worthless. Talk about a major flop. Then there's the classic case of the thief who tried to snatch some cash from a bank. In his rush to get out, he grabbed a bag full of bills, completely clueless that it was rigged with die packs. The second he stepped out of the bank, boom! The capsule exploded, covering both the cash and the crook in bright, unmistakable dye. Those bills became totally useless, and the mastermind left a literal trail of evidence straight to where the cops nabbed him. Honestly, I bet that trail wasn't just bright red or purple. There was probably a little brown in the mix too. Not that the press would mention that part.